morning, everybody. The topic of my thesis is resource allocation and power control of device-to-device communication. Since the number of mobile subscribers are increasing day by day, and not only the mobile subscribers are increasing, but the applications also getting at once. So there is need of high spectral efficiency. In order to cope the requirement for high spectral efficiency, we must need some techniques that can reuse the spectrum efficiently. So, device-to-device communication is one of the possible remedies, which is the most fascinating techniques nowadays. Here we have proposed some schemes for interference management. Because the device-to-device communication is reusing the cellular spectrum, so interference is no longer negligible. We have proposed two schemes for interference management. The first scheme is joint resource allocation and power control, which we have called GRP scheme. And the second scheme is separate resource allocation and power control. Here is the old system model. Our system model is composed of two cells. The blue cell here contains two device-to-device gears. We also call this D2D gears. And both the cells contain some cellular users that are randomly placed in it. We have divided the entire spectrum into some resource blocks, where each resource block occupies one of the cellular users from one cell and one of the cellular users from the other cell. You can see here an animation. We also have D2D links, and each D2D link can occupy any of the resource blocks being occupied by cellular users. So here we have the objective problem. Our primary problem is to minimize the power being consumed by the cellular user and the D2D user with certain constraints. And the constraints are, C1 is the upper bound power constraint for both the cellular users. C2 is the upper bound power constraint for D2D users. And C3 is the rate target constraint for D2D user. C4 and C5 are the rate target constraint for the cellular users. And C6 is the orthogonality constraint, which means that two D2D users cannot occupy the same resource block at a time. So we have proposed two schemes for our interference management. The first scheme is GRP scheme, or joint resource allocation and power control scheme. The other scheme is the SRP scheme, which is the separate resource allocation and power control scheme. Since our problem is multi-resource block problem, and it obeys the time sharing condition, which means that if you are increasing the number of resource blocks, the duality gap, which is the difference between the solution of primary problem and the solution of the dual decomposition problem, that gap decreases. Ideally, the gap should be zero. So it's obviously not possible to make that gap equal to zero, because if you are increasing the number of resources left, our problem is anti-Hart problem, and the complexity grows exponentially with the increase of resource blocks. So for each resource block allocation, we have an associated Lagrangian associated formulated problem, which is given by this equation. This is the rate constraint and this is the power constraint here. So here is some mathematical work. It can be further elaborated with this picture. First of all, the GRP scheme, we solve for each of the resource block with all the constraints. This problem we solve with all the constraints for separate blocks, and as you can see here in this equation C. After solving for each block separately, then we sum up all of these in equation A. And then we not only get the optimal solution, the lower bound for the optimal solution, but we also get the GRP solution. And what is GRP and what is the optimal solution, we will see it in the simulation result. This is the joint resource algorithm for sub-problem, where each resource block, the solution for each resource block with given constraint. And since while we are solving this algorithm, there are some Lagrangian multipliers that need to be updated. And we have used the subgradient method, this one, the algorithm 2, to update our Lagrangian multipliers. And this is the whole GRP algorithm, where we first accumulate for all the resource blocks separately, independently, and parallel. Then we sum up all of them, and finally we get the lower bound for the optimal solution. That we compare with the SRP scheme and GRP scheme, and we see that how far we are from the optimal solution of the problem. The other scheme that we have proposed a separate scheme for resource allocation and power control. And this scheme, the entire resource block is scanned by a separate D2D link, where and whenever a D2D link finds a resource block power efficient, it will put a small stake of rate contribution over there. And this one goes on and on until our iteration is finished. Then we have the resource allocation algorithm. The resource allocation, this is the power control algorithm, where a single D2D link is scanning for a certain amount of iteration all the resource block and will put some small rate contribution, and that rate contribution will accumulate on and on. And when this is finished, when the iterations are finished, then we have the resource allocation algorithm. And resource allocation algorithm, wherever we have high rate contribution, it means that that resource block is more power efficient, and then that D2D link will be assigned to that particular block. Also, the resource allocation algorithm maintains some fairness of resource block distribution among the D2D links. It will be further elaborated with this given example as we mentioned in system model. Here we have two cells where each cell occupies some single user, and the single user preoccupies this resource blocks here as you can see. And we have two D2D links. So we have three resource blocks, two D2D links. The D2D link 1 and D2 will scan for the first iteration. The D2D links 1 find this one, first resource block more power efficient, so it will put small rate contribution over there. And for this one was more power efficient, so it will put small rate contribution here. For the second iteration, you can see that one, the third was more power efficient, so it will put the small rate contribution here, and for this one, this. And this one goes on, and as long as it can find some high power efficient, low power hungry resource block, it will put its rate contribution over there. So you can see for this one, this resource block was more power efficient or less power hungry. So it can assign this resource block to this one, and for that one the brown is more power efficient, so that will be assigned to that one. Now we have 3 resource block and 2 D2D link. Now this one is remaining. As you see here, it has only 1 rate contribution for the black one. However, there are 3 rate contributions, so it means that one was more power efficient for the blue one as compared to this one. So that one will also be assigned to the blue one. This second resource block will also be assigned to the blue one. Now let's further elaborate the example. Suppose we have, how can we maintain the fairness of resource block distribution among the D2D links? We can distribute the number of resource block as given by this formula, number of resource block divided by D2D links. But here is the fractional number. In order to divide the fraction, we can assign the minimum number of resource block to D2D link and the maximum number of resource block to D2D link. Suppose we have 10 resource block, that means that for 3 D2D links, 2 of the D2D links will take 3 resource block, and 1 of the D2D link will take 4 resource block. Here you can further see an example. The D2D link one will scale for the entire resource block for all the iteration, and the rate contribution will get, we will get somehow like this. Likewise for D2D link 2, it will scale for the entire resource block, and we will get the rate contribution like this. No, we will just finish, so just eliminate the low rate contribution blocks because it's not anymore required. Here you can see there is violation for orthogonality. So and also you can see that this one is this seems to be a bit higher than this one. So the upper one will be finished, and we will get with 3 plus 4 plus 3 because the 10 resource blocks that are equally distributed on 3 D2D. And sometimes we can have a case that for D2D links, for most of the time the resource blocks will be more power efficient. So here you can see, although the red one you can see it is more power efficient than this one, the green one. But that one is exceeding the maximum number of that can be allocated to D2D link, because at most we can allocate 4 resource blocks. So obviously the red one will be eliminated, and we will left with only 4 plus 3 plus 3 equal to 10 resource blocks. Here we go. Here are the simulation results, and we have got these numericals from a standard research paper. So we have done two things. For the first case, we have kept the D2D rate target constant, and we are keep varying the cellular rate target. And we are looking at how the transmitting power is influenced with this. As our D2D distance is very less, then we can see that for lesser D2D distance, here you can see it is for D2D distance at 30 meter. And the black one is the lower bound for the optimal solution, which we got from GRC scheme. It is more power efficient, and it means that the transmitting power will be very less in this case. But as you are increasing the rate target on cellular user, this will increase. The transmitting power will also increase. And you can see here the GRP scheme is quite closer to the optimal solution. You can see that the blue one is the GRP solution and the black one is the optimal solution. However, the SRP scheme, which is quite simpler but not that much efficient as much this one blue scheme is. And as long as we are increasing the D2D distance, you can see here we have increased the D2D distance, so the transmitting power has been increased here. With the black one is the lower bound for the optimal solution. The blue one is just the distance between GRP scheme and the lower bound, and this one is for the SRP scheme. Sometimes we also have cases where our constraints are violated, and we call this infeasibility. Here you can see for GRP scheme is always less infeasible as compared to SRP scheme, and then this is for 30 meter and this is for 50 meter. This is the final result. Now, vice versa, we have done we have kept our cellular rate target fixed, and we are keep on varying the rate targets on D2D user. So it is much more influence if the D2D user are close to each other. You can see here the transmit power is not increasing tremendously. And this is the black one. It is the lower bound for the optimal solution. GRP scheme still it is looks very good, but the SRP scheme, as we are increasing the D2D rate, it is getting departed more and more, and it get worse. However, for the 50 meter, you can see that even the blue will get more departed as we keep on increasing the D2D rate target. So it will be influenced if you are increasing the D2D distance more and more. And the greater power will be required if the greater power required for per block, per resource block. That means that interference will not be that much negligible. We are increasing the interference. In this case, you can see this infeasibility. Here the constraints again, in GRP scheme, the constraints are less violated as compared to SRP scheme. And this is for 50 meters, and these two are for 30 meters. Finally, here is the conclusion. We have proposed two schemes. One is the GRP scheme and one is the SRP scheme. The GRP scheme, it is quite seems quite good, quite sophisticated, but the problem is it is very complex. If you are increasing the number of resource blocks, it gets more and more complex. And it takes much more time for simulation. The other one is the SRP scheme, which is quite simpler, but its performance is not that much efficient as much GRP scheme is. So there is trade-off between the complexity and performance. In future, we are focusing to either to improve the efficiency of SRP scheme with this simplicity, or we have to increase the GRP scheme. We have to reduce the complexity of GRP scheme with this kind of performance. Thank you. Any questions?
Questions?